In this video, we're going to derive the Friedmann-Lemaitre-Robertson-Walker metric, also called the FLRW metric for short. This is the metric that describes the expansion of the universe over time, which is used in the standard model of cosmology. The FLRW metric was discovered and developed independently by 4 different physicists, and so the metric is named after all of them. The FLRW metric is actually 3 metrics combined into one, depending on the value of k, which is +1 for a closed universe, 0 for a flat universe, and -1 for an open universe. In later videos, we'll use the FLRW metric to derive the Friedmann equations, which directly govern the rate of the universe's expansion based on mass density, pressure, curvature, and the cosmological constant. So our goal for this video is to derive a metric that describes the large-scale geometry of the entire universe, and this will be the FLRW metric. This metric can be derived from one fundamental assumption about the nature of the universe. This fundamental assumption is called the Cosmological Principle, which has 2 parts. The first assumption of the Cosmological Principle is that the universe is spatially homogeneous. This means that the universe looks the same from all points in space. You can think of this as meaning that the universe doesn't appear to change when we translate our location from one spatial point to another. This also means that the universe has no spatial center, since all spatial points are equivalent. The second assumption of the cosmological principle is that the universe is spatially isotropic, and this means that the universe looks the same in all spatial directions. You can think of this as meaning that the universe doesn't appear to change when we rotate our frame of reference. Now, you might say that these 2 assumptions are obviously false. After all, our solar system has the burning hot sun, a few planets, many asteroids, and lots of empty space, depending on where you look. So it's obviously not the same at all locations and in all directions. But when we say the universe is homogeneous and isotropic, we're talking about the universe on average at the largest scales. If we zoom out from our solar system, we'll see our galaxy, then galaxy clusters and superclusters, and then the web-like galaxy filaments. At these huge scales, we can divide the universe into boxes that are hundreds of millions of light years wide. And at this large scale, most boxes look basically the same. So when we make the assumption that the cosmological principle is true, we're assuming that the universe looks the same at all points and in all directions, on average at the largest scales. I said earlier that the FLRW metric covers 3 metrics in one. These match up with the 3 possible spatially homogeneous and isotropic universes, which are the closed, flat, and open universes. Now, from a mathematical point of view, there are actually other geometries that are spatially homogeneous and isotropic, such as a flat geometry that wraps around at the edges and makes a torus shape. However, in this video, I'm going to ignore the more complicated geometries that have holes in them. So I'm only going to consider the simply connected geometries without holes, and in this case, there are only 3 possible options. To start, let's focus on the familiar flat space case first. The metric for flat spacetime is called the Minkowski metric. We know that in Cartesian coordinates, the flat Minkowski metric looks like this, and we're using the mostly minus convention here. If we describe flat spacetime in spherical coordinates instead, the Minkowski metric looks like this. Let's think about how the Minkowski metric would change if we assume that the cosmological principle is true, and the universe looks the same at all points in all directions at the largest scales. Well, notice that the cosmological principle says that the universe is spatially homogeneous and spatially isotropic. It doesn't say that the universe is the same over time. So according to the cosmological principle, we can allow the scale of space to change over time. We do this by scaling space by a factor a of t that depends on time. This has the effect of multiplying the 3x3 spatial portion of the metric by a of t squared, since the spatial metric components are the dot product of two spatial basis vectors. And we're forced to multiply all the components in the spatial part of the metric by the same factor because we need to treat all directions as equivalent, since the universe is spatially isotropic. So this metric describes a flat space whose scale changes over time according to the scale factor a of t. Taken as a whole, this 4x4 metric represents a curved space-time, described by a non-zero Riemann curvature tensor. But when we look at the 3x3 spatial part of the metric at a given instant of time, this 3x3 metric represents a flat space, with a spatial Riemann curvature tensor that equals 0. So even if the individual spatial slices in this metric are flat, spacetime as a whole is curved, provided that a of t is not constant. So a flat 3D space whose scale is changing over time with a scaling function a of t is one possibility for a universe that's spatially homogeneous and isotropic. But that's not the only option. There are two other choices for spatially homogeneous and isotropic universes, which are the closed universe, also called the spherical universe, and the open universe, which is also called the hyperbolic universe. Let's look at the case of a spherical universe first. If we look at the familiar two-dimensional spherical surface, all points on the sphere are basically equivalent, and they are basically the same in all directions. So, just like the flat plane, the sphere also meets the criteria of being spatially homogeneous and isotropic. But our universe is spatially three-dimensional, not two-dimensional. So how would we describe a three-dimensional sphere mathematically? Well, we know that the equation of a circle, sometimes called the one-dimensional sphere, in the xy plane is given by x squared plus y squared equals r squared, where capital R is the circle's radius. We can also parameterize the circle by the parameter theta, where x equals r times cosine theta and y equals r times sine theta. If we plug x and y into this formula and factor out r squared, we can use the trig identity cos squared plus sine squared equals 1 to find that this equals r squared. So this parameterization involving theta satisfies our circle equation. The equation of the two-sphere in 3D space is x squared plus y squared plus z squared equals the radius squared. We can parameterize the sphere in terms of theta and phi. We can think of theta as selecting an x-coordinate on the sphere. And we can think of phi as tracing out a circle of radius r times sine theta at that specific x-coordinate. If we sub this parameterization into x squared plus y squared plus z squared, we can factor out r squared, factor sine squared, and collapse this to a 1, and collapse this to a 1 to get r squared as expected. So this parameterization satisfies the two-sphere equation. Now, the equation of a three-sphere in 4D space is x squared plus y squared plus z squared plus w squared equals the radius squared. We can't really visualize this easily with a drawing, but we can parameterize the three-sphere in terms of three angle coordinates, theta, phi, and chi. To get these, we can follow the pattern for the parameterizations for the one-sphere and two-sphere. The first coordinate is r times cosine theta. For the next coordinate, we turn cosine into sine and add cosine phi on the end. For the third coordinate, we turn cosine into sine and add cosine chi on the end. And for the fourth coordinate, we turn cosine into sine. We can confirm that this parameterization satisfies our three-sphere equation by factoring out r squared and collapsing all the cosine squareds plus sine squareds to 1s. We can use these formulas for a sphere in any dimension. and we can always follow a similar pattern to get the parameterization for that dimension. But our spatial universe is three-dimensional, so we're just interested in the three-sphere. Recall that the basis vectors for our coordinate system are just the partial derivatives with respect to the coordinate variables. We can write these basis vectors in terms of the x, y, z, w basis vectors using multivariable chain rule. And if we work through all these partial derivatives, we get these formulas for the basis vectors. Now, there are two different metrics we can use to analyze the geometry of the three-sphere. We could use the extrinsic XYZW metric of the surrounding four-dimensional space. And this is just the 4x4 identity matrix, or Kronecker delta, since the XYZW basis is Euclidean and orthonormal. Or we could use the intrinsic metric, which only uses the angle parameters theta, phi, and chi, where the metric components are the dot product of the theta, phi, chi basis vectors. If you work through all these dot products, the off-diagonal metric components go to 0, and the diagonal metric components look like this. So this is the intrinsic 3x3 metric of the three-sphere. If you take this metric and go through the process of calculating the Ricci scalar for the three-sphere, you'll find that it's a constant positive number everywhere, 6 over r squared, where r is the sphere's radius. A constant Ricci scalar is exactly what we'd expect for a space that's homogeneous and isotropic. Now, since the names for these three angle coordinate variables are arbitrary, I'm just going to relabel them so that they look like this. And now we see that the metric for the three-sphere almost looks like our flat metric in spherical coordinates, but with the r coordinate replaced by sine of chi. So we have a metric for a universe that is spatially flat, and another metric for a universe that is spatially spherical. The third type of metric that is spatially homogeneous and isotropic is the metric for hyperbolic space. Hyperbolic space is a little bit more difficult to visualize, but I'll do what I can to show you what it looks like. So the two-sphere, S2, is a space where every point looks like two frowns crossing each other if we're standing on the outside of the sphere, or two smiles crossing each other if we're standing on the inside of the sphere. The hyperbolic plane, H2, is a space where every point looks like a frown and a smile crossing each other. So in H2, each point looks like a saddle point. When we look at a circle of a given circumference, in flat space, the area and the circumference of a circle are given to us by the standard flat space formulas. On a sphere, a circle with the same circumference has an area that's greater than what we'd see in flat space, because the space bulges out and increases the surface area. In the hyperbolic plane, a circle with the same circumference has an area that's smaller than what we'd expect in flat space, because the circumference wastes a lot of distance going up and down around the saddle point, and it doesn't enclose as much area. The equation for the two-dimensional hyperbolic plane is x squared plus y squared minus q squared equals negative r squared. Alternatively, we could multiply both sides of the equation by -1 to get q squared minus x squared minus y squared equals r squared. This gives the equation of a two-sheeted hyperboloid. We can parameterize this surface with angles chi and theta, where the hyperbolic cosine of chi selects the q-coordinate of the surface, and theta traces out a circle of radius r times sine h of chi in the xy plane. Now, even though we can draw this hyperboloid surface, this is not a true representation of the hyperbolic plane, because the distance function for measuring distances on this hyperboloid are not Euclidean distances, because the metric signature has minus signs in it. So we cannot accurately judge distances on this surface using our eyes. because the metric we're using to measure distances is not Euclidean. The hyperbolic plane is usually visualized using projections of various kinds, where the distances and sizes of objects are distorted. This drawing by Escher is one of the most common visualizations of the hyperbolic plane, where each fish or triangle occupies the exact same area, according to the hyperbolic metric, even though it doesn't look like it to our eyes. I've linked to another video in the description that does a really good job of helping visualize hyperbolic space. With that said, the chi-theta parameterization can be substituted into our qxy formula for hyperbolic space. After factoring out r squared and factoring sine h squared, this goes to 1. And using the hyperbolic trig identity, cos h squared minus sine h squared equals 1, this becomes negative r squared as expected. Now, to get the formulas for hyperbolic 3 space, we can just follow the pattern like we did before. The first coordinate variable equals r times cos h of chi. Then we change cos h to sine h and add a cosine on the end. Then we change cosine to sine and add a cosine on the end. Then we turn cosine into sine. If we plug this parameterization into our formula for hyperbolic 3 space, after factoring and canceling, we end up with negative r squared at the end. So this parameterization works. So no matter what the dimension of hyperbolic space we're looking at is, we can always use the same pattern to find out the parameterization. But for our purposes, we're only interested in hyperbolic 3 space. As before, we can get the basis vectors for chi, theta, and phi by expanding them in terms of the q, x, y, z basis vectors using multivariable chain rule. And as before, we can use the extrinsic 4x4 metric with q, x, y, z to measure distances. Or we can use the intrinsic 3x3 metric with chi, theta, phi. Just like before, the off-diagonal metric components go to 0, but the diagonal components now look like this. If you calculate the Ricci scalar for hyperbolic 3 space, you'll find that it's a constant negative value everywhere, -6 over r squared. Again, a constant Ricci scalar everywhere is exactly what we'd expect for a space that's homogeneous and isotropic. So this is what our metric looks like for hyperbolic 3 space. It looks the exact same as the metric for the 3 sphere, except the sine term is replaced with a hyperbolic sign. So we now have 3 different metrics for the 3 possible homogeneous and isotropic spaces. The spherical space, also called closed because the space is finite, the flat space, and the hyperbolic space, also called open because it goes out to infinity. And for consistency, I'm going to replace the flat space's r variable with chi. We can now insert these 3x3 spatial metrics into the spatial part of our 4x4 spacetime metrics, where the spatial parts are multiplied by the scaling factor a of t, which is consistent with a spatially homogeneous and isotropic universe. I'm also ignoring the capital R parameters for the spherical and hyperbolic geometries, since that's a constant that can be absorbed into a of t, which basically plays the same role of telling us how curved the space is. These 3 metrics are basically the exact same, except for the role of the chi-coordinate. The chi-coordinate is sort of like a radial coordinate that points out from the origin of the coordinate system, although chi doesn't measure the true distance from the origin. For a closed universe, chi is the circular angle measured outward from the origin, and for an open universe, chi is the hyperbolic angle measured outward from the origin. It's also important to remember that, since the scale of the universe is changing over time with the scale factor a of t, the actual distance represented by 1 unit of chi is also changing over time. Mathematicians have actually come up with a trick to write down all 3 of these metrics using a single unified metric. And this is done by introducing a parameter k, which is either +1, 0, or -1. We can do this by rewriting the chi terms as the variable r. So for a closed universe, r equals sine of chi. For a flat universe, r equals chi. And for an open universe, r equals hyperbolic sine of chi. So what we're doing here is we're basically doing a change of variables where the ct, theta, and phi coordinates stay the same, but the chi coordinate is rescaled to a new coordinate called r. Remember, basis vectors are just the derivative operators with respect to coordinate variables. So to convert between a chi basis vector and an r basis vector, we use the chain rule conversion term, dr by d chi. If we look at this derivative for each of the three universes, we get cosine of chi for a closed universe, 1 for a flat universe, and hyperbolic cosine of chi for an open universe. In terms of the metric components, grr equals er dot er, and g chi chi equals e chi dot e chi. So the conversion factor between them is the square of this derivative. For the closed universe, cosine of chi squared is just 1 minus sine of chi squared. And since sine of chi is just r, this is also equal to 1 minus r squared. For a flat universe, we just leave 1 squared as 1. For the open universe, cos h of chi squared equals 1 plus sine h of chi squared. But since sine h of chi is just r, this becomes 1 plus r squared. So we can rewrite all three of these conversion factors using the form 1 minus k r squared, where k is plus 1 for a closed universe, 0 for a flat universe, or -1 for an open universe. So what we've learned is that to convert from the grr metric component to the g chi chi metric component, we multiply by the square of this derivative, which is 1 minus kr squared. And going in the other direction, from chi to r, we divide by 1 minus kr squared. So to change our metric from using the chi coordinate to using the r coordinate, we divide the g chi chi component by 1 minus kr squared to turn it into the grr component. Then we replace the various chi functions with r, as we've defined up here. The resulting metric describes all three spatially homogeneous and isotropic universes, with a spatial scale factor a of t that can change over time. This is the FLRW metric, which can describe an expanding universe. Before the end of the video, I'll say one more thing about this coordinate change from chi to r that we did, which will hopefully make things more clear. For the closed universe, the chi theta phi coordinates are all circular angles used to identify a point on the 3-sphere. These are called hyperspherical coordinates. After defining r as sine of chi, the r theta phi coordinates are called reduced-circumference polar coordinates. On the 3-sphere, the chi coordinate is the angle from the North Pole to a specific point. We can think of this point as lying on the edge of a disk with a radius small r. Looking at this triangle, we can see that r equals the sine of chi, which is the definition we made earlier. And this red disk containing the point has a circumference of 2 pi r. Similarly, for the open universe, chi is a hyperbolic angle and all the other coordinates are circular angles. And we can define r as sine h of chi. If we look at the hyperboloid sheet, chi is the hyperbolic angle of a point measured from the vertical axis. Looking at this triangle, we can see that the radius small r of the red disk is sine h of chi, as we defined previously. And the circumference of this disk is again 2 pi r. So with the r coordinate, we're not measuring the true walking distance from the origin to a point in the curved space. Instead, we're drawing a circle around the origin containing that point with a constant radius. And we define r to be the radius of a flat disk containing this point. r is called the reduced circumference coordinate because it's defined by taking a circumference around the origin and dividing it by 2 pi. So again, the r coordinate is not the walking distance radius from the origin to a point in curved space. Instead, r is the circumference of a circle containing that point reduced by a factor of 2 pi. We actually saw something similar for the Schwarzschild coordinates in video 108b, where the r coordinate is equal to a circle's circumference divided by 2 pi. So the Schwarzschild r coordinate is also a reduced circumference coordinate, not a true radius. So that's it for this video. In the next video, we'll compute the various tensors in the Einstein field equations that come from the FLRW metric. And this will help us solve for the motion of free particles in an expanding universe.